Okay, so you know what we'll do is we'll learn how we can find efficient allocations in alternative ways. So one of the ways is the following, that solution to the following problem yields the Pareto efficient allocation. Okay, so consider any alpha between 0 1. Okay, and the optimization problem is defined as follows, which is maximize with respect to choosing an allocation, okay, x1 y1 x2 y2 from the feasible set of allocations. We want to choose that allocation which maximizes the weighted sum of utilities of the two agents. Okay, so alpha times u1 x1 y1 plus 1 minus alpha times u2 x2 y2. Okay, so you want to choose a feasible allocation that maximizes this. Okay, so it turns out that when you solve this optimization problem, the solution to this optimization problem will be a Pareto efficient allocation. Okay, and as you change alpha, you'll get a different Pareto efficient allocation. So you'll get the entire set of solutions, which of course vary with alpha, and the union of all such solutions will be actually a subset of set of efficient allocations for the exchange economy. Okay, so this is what we are going to prove. Okay, we'll prove that consider any alpha between 0 and 1, and look at this optimization problem. Solution to this problem will be Pareto efficient. Okay, so solution to this problem is Pareto efficient. Okay, please note that I'm not saying that you will get the entire set of efficient allocations. It is possible that some of the efficient allocations uh, may not be the solution to any problem of this type, for any alpha, so it's possible. Okay, but you will get a very considerably big set. I mean, if you just solve this optimization problem. I'll also tell you, there is this uh, another good thing about this particular result is that it can be generalized to you know any number of consumers and any number of goods. Okay, so this is also something which is true about it. And there is another thing which is also true. If you can also take monotonic transformations of utilities, while you are solving this problem. You can also consider different monotonic transformations of u1 and u2 and then solve this particular problem. They'll also generate Pareto efficient allocations. Okay, so this is actually kind of a very neat result, and it can be used to actually find out efficient allocations. Okay, so let's see how we can do it. Okay, so but before that, let me first prove this. Okay, so let's call this is a proposition, and here is a proof. So what I'm going to do is I'm going to show that if something is not Pareto efficient, then it cannot solve this problem. Okay, so this is a way to prove it, because I want to show that if something solves this problem, if x1 star y1 star x2 star y2 star solves this problem, then x1 star y1 star x2 star y2 star is Pareto efficient. This is what I want to prove. So it's a conditional statement. So another way to prove it is basically you can prove it's contrapositive. So what is the contrapositive of this? That if a particular allocation, a particular feasible allocation is not Pareto efficient, then that feasible allocation cannot be the solution to any problem of this kind. Okay, so that is what we just need to show. Okay, so let's prove it. So suppose x1 prime, y1 prime x2 prime y2 prime is not Pareto efficient. Now what do I want to do? I want to show that then this cannot be the solution to any problem of this type. Okay, so how will I show this? Uh, that's straightforward. Use the fact that it is not Pareto efficient, so there must exist, so there must exist a feasible allocation x1 double prime y1 double prime x2 double prime y2 double prime in the feasible set. Okay, so there must exist some feasible allocation like this, such that if you compare this allocation with this particular allocation, so let's call this prime allocation, let's call this double prime allocation. Okay, so if you compare double prime allocation with prime allocation, then moving from prime allocation to double prime allocation will make at least one of the consumers better off without making the other one worse off. Okay, so how do you write that? This is how you can write it, that such that either this is true, either u1 x1 double prime y1 double prime is greater than u1 x1 prime y1 prime, and u2 x2 double prime y2 double prime is greater than or equal to u2 x2 prime y2 prime. So basically, either you can make one better off without making two worse off by moving from prime to double prime allocation, or you can make two better off without making one worse off. So how do you write that? This is how you can write it. Okay, now notice that if these conditions are true, so either this is true or that is true, then if I multiply both sides by alpha, so let's just multiply alpha here, alpha here, and just multiply 1 minus alpha both sides, the inequalities will be preserved, right? Okay, now if you add left hand side of this to the left hand side of this and compare it with the sum of the right hand sides, so then this implies that alpha u1 x1 double prime y1 double prime plus 1 minus alpha u2 x2 double prime y2 double prime must be strictly greater than alpha u1 x1 prime y1 prime plus 1 minus alpha u2 x2 prime y2 prime, no matter what alpha is. Okay, no matter what value of alpha you consider, for all values of alpha between 0 and 1. So what that means is, no matter what happens, x1 prime y1 prime x2 prime y2 prime cannot be the solution to this problem, because there exists a feasible allocation which will yield a higher weighted sum of utilities, right? I mean, this is a higher weighted sum of utilities than this one. So if something is not Pareto efficient, if an allocation is not Pareto efficient, then it cannot solve a maximization problem like this. Okay, which simply means that if something solves a problem like this, then it must be Pareto efficient, right? That's a proof. If a feasible allocation solves this problem, then it must be Pareto efficient. This is what we have proved. by this very simple set of arguments. Okay, so this is something that we'll use and solve this optimization problem. Please note that even though I've written alpha 1 minus alpha, but you can also write alpha beta if you wish. It's the same thing, because what you're doing is you're just maximizing this whole thing. You're just multiplying this. Sorry about that. You're just multiplying this whole thing by, if you take this to be if you want this to be 1 minus alpha, then you are just taking the monotonic transformation, which is 1 upon alpha plus beta, because then this will become alpha upon alpha plus beta, and this will become beta upon alpha plus beta, which is the same thing as saying that this is alpha times this and 1 minus alpha times this. So the weights may or may not sum to 1. The point is, uh, the point here is this, that because anything like this can be written in an equivalent way, which is alpha 1 minus alpha. That is why I chose alpha 1 minus alpha. But even if you take the weights that don't sum to 1, that's also okay. It doesn't matter. Is that okay? Because you'll get the same set of solutions. Have you all understood this? For different alphas, of course. So this problem is identical to this problem. Basically, let me just tell you, this problem is identical to this problem. Because all that you have done is, just to make sure that the sum of weights is 1, you have divided this by alpha plus beta. Okay, so the solution to this problem will be same as solution to this problem. Yes or no? If you maximize this, subject to the feasibility constraint, subject to choosing a feasible allocation, you'll get the same solution as you're going to get with, because you just divide the entire objective by alpha plus beta. It's not going to make any difference. Is that clear? Okay. Okay, so one very nice thing about this result is that if you want to prove, that okay, a particular allocation is Pareto efficient, then this could be one way in which you can prove, that you can actually find alpha, you know, such that um, such that the weighted sum of utilities, if you solve the maximization problem, where alpha is your weight to u1, 1 minus alpha is your weight to u2. Okay, if you solve this maximization problem with weighted sum of utilities, the solution will be that allocation. So if you can find such alphas, then obviously it's a proof that the allocation is Pareto efficient, right? Okay, so that is one very nice thing about this. So anytime you are given a problem, okay, check if show that a particular allocation is efficient, you can try this. But as I've said, that these are not sufficient conditions. This is a sufficient condition. This is not a necessary condition. Okay, so it is possible that some Pareto efficient allocations may not be, for those allocations, it may not be the case that such an alpha exists. Okay, so then you'll have to try other ways to check for efficiency. But this is something that will work in many cases. And if you are going to use it a little bit more clever way, then you can even consider, instead of maximizing this objective, you can also consider maximizing these kind of objectives. So if you just use it in a clever way, you can actually consider maximizing the objectives of this type, where f1 is a strictly increasing function and f2 is a strictly increasing function. So that will give you access to even more solutions. give even more efficient allocations. I mean, because solution to this problem will also be, if F1 and F2 are strictly increasing, solution to this problem will also be a Pareto efficient allocation. And the proof is just identical. You just have to replace, uh, U1 by F1 U1 and U2 by F2 of U2. That's all that you have to do, and the entire proof goes through. Okay, so basically what that means is, and this is true for every F1, every strictly increasing function F1 and every strictly increasing function F2. So that means there is a lot of scope to actually figure out, to establish, whether a particular allocation is Pareto efficient. I mean, by thinking about different F1s and F2s. And it is also possible that your utilities are of the type that even this is sufficient. This might just give you all the efficient allocation, and there is no need for F1 and F2. That's also possible. But the point here is this, that this is a sufficient condition. Any problem like this, if you solve it, yes, F1 and F2 are strictly increasing functions, so therefore these are monotonic transformations of utility functions. Okay, F1 U1 is a monotonic transformation of U1, F2 of U2 is a monotonic transformation of U2. That's right. Okay, so so there is a lot of scope here, to actually uh, pin down all efficient allocations. Okay,